Hello everyone. Today I'm going to present our work, Federated Secure Data Sharing by Edge Cloud Computing Model, authored by myself, Arijit Karati and Sajal Kedas. I sincerely thank the organizing committee members for accepting our work at the IEEE Globecom 2022 conference. In this work, we'll discuss a secure edge cloud paradigm and a safe data sharing technique using the key aggregated crypto system. Here are the contents of this presentation. First, we'll talk about edge-based cloud-assisted data sharing and point out the shortcomings of the current methods. Then I discuss the purpose and significance of our work. After that, I'll illustrate the proposed solution in detail. Next, I'll explain the adversary model and certain security assumptions to show the proposed scheme is secure against all the known security hurdles. Finally, we'll review performance estimation, comparisons, and empirical results. Technology has diligently optimized the gaps in human-machine interaction over several decades. Edge computing as a modern innovation improves user experience by putting hosting service, workloads, and vast quantities of data at the network's edge. Here, figure 1 depicts the scenario where users are in a potent edge-assisted cloud environment and data flows seamlessly from one cloud to users' proximal locations. The edge between the cloud and the users executes specific activities to minimize the cloud overhead. Typically, the edge controller is considered in this system who monitors such edge devices. When a user uploads a file to a specific cloud, an edge devices on the consumer's request download such file from the cloud and store it at the edge for future use. Here, there could be several security issues. For example, federated access control by the user and edge devices, data confidentiality against cloud and semi-honest edge devices, users' authenticity during downloading multiple files from multiple clouds, and also user revocations. In edge computing settings, several research works have been carried out. Despite their individual benefits in data caching, data transmissions, lightweight protocol, most of such schemes do not discuss any specific security issues. Besides, such approaches are built for a single use case and may not be relevant to other edge-based setups, posing integration and security hurdles, particularly when several semi-honest or fully vulnerable receivers download multiple data from multiple clouds. Therefore, we observe that federated security and its privileges are confined to edge devices. Specifically, an edge or intermediate device is with limited permission on deciding consumer access, while the owner has almost full control over whether to grant access or not. Even if an edge device flags a user as malicious, cloud data might be bypassed at the edge layer and decrypted by an insider attacker for a valid secret key. This is because the owner assigns decryption privileges and the edge controls only the user's subscription. Hence, edge layer cannot prevent harmful actions until the owner takes a specific action. This motivates us to pose a question: can we design an edge-assisted cloud-based data sharing system where data is shared across multiple clouds under several file classes and authorized subscriber can download them anonymously and securely through nearby edge devices without knowing the specific file locations? Therefore, our contributions are as follows. Strong privacy protection on confidential data. Data confidentiality is provided under specified file classes using the key aggregated crypto system. Besides, we have introduced anonymous authentication during downloading any remote files. Fine-grained access control and user revocation. Access credentials are distributed among several entities rather than a single authority. Therefore, even if the attacker bypasses the edge, it cannot decrypt the data. Besides, the controller revokes user functionalities for any kind of misbehavior activities treated as insider attacks. No file location required to download. Nowadays, people deal with numerous files and store them in different clouds. Our protocol facilitates the consumers not to remember where the queried file exists. Certainly, it enhances the privacy of the cloud as the receiver doesn't know the data is coming from which location. We achieve these features by the name data networking. Apart from that, the KSE has some other features like it receives higher security notions, it supports multiple cloud platform integration, and also it reduces the computation cost, transmission cost, and the storage cost. The proposed work is named as KACEC protocol, which considers several algorithms such as key issuance, file encryption, file request, extract, data request for file class I, authorization, key transform, and file decryption. Now we discuss issuing certain cryptographic keys. Figure 2 depicts the key management process in the proposed KACEC protocol. Initially, the data owner uploads several files based on different file classes, and consumer can only decrypt such files if he or she has a valid set of secret keys. For this, we have assumed KGC as a semi-trusted entity. So initially, for some security parameters, KGC generates public parameter params and then safely save that MSK in its storage space. After that, for each user, KGC issues a set of keys based on different file classes assigned by the data owner. And after that, it transmits, transmits this USK back to the consumers. Next, KGC issues a partial private key for which the controller generates its private control key and builds its own public key, PKCNTRL. After that, the controller issues a set of public key private key for each and every edge device. The remaining tokens or the remaining keys are generated during the data transmission, which will be discussed in the next slide. Figure 3 discusses the data sharing process in the proposed KACEC protocol. Initially, data owner chooses a file and encrypts using symmetric encryption. And then it encrypts the symmetric key using our proposed KAC encryption. And finally, it uploads the data to a specific cloud platform. In order to download such file, consumer requests for such file to its nearby edge device with some request token. This request token basically considers two different keys. First key is temporary key and the second one is one access token. On receiving such request, edge device authenticates that customer anonymously and fetches the file address. With this file address, it searches for that file in its local space. If it is present, then it can directly send that data back to the consumer. If it is not present, then it forwards the data to the Indian platform, which is connected to the cloud platform. Eventually, with the help of Indian, each device receives such file. After that, it checks whether the file is designated for such consumers or not. For such kind of feature, uh, it uses some secret keys and generates some token, and that token is named as AK. Now, this AK can be null or it can be some valid keys. After this, ED makes the encrypted data ready for the consumer. For that, ED uses its again the secret key and incorporates the missing credential which will be required to decrypt such encrypted file by the customer. And for this, it performs certain verification, authorization related verification, and finally uh, produces omega prime, that is the final data, and sends this data to the consumer. Now, the consumer receives such file and applies the proposed KCEC decryption algorithm and reveals the symmetric key and uses this symmetric key to perform symmetric decryption over the ciphertext and gets back the message. Now we'll discuss about the security analysis of the proposed scheme, threat model and assumption. Data can be compromised in many ways. For instance, uploaded data may be tampered with by several clouds, edge devices, end users, or even any untrusted entity during open transmission. Several attackers, as depicted in Figure 1, engage in breaching the reliability are divided into two different types, malicious and semi-honest attackers. In a typical scenario, malicious activity may be observed at the end user level, while the semi-honest adversary are at the edge and cloud level. We list the adversary's capability and certain assumptions below. The controller is expected to be a powerful and trustworthy entity that provides services to its subscribers via edge devices. Therefore, end users are unable to engage directly with the controller during any data transmission. User registration takes place over a secure channel using TLS protocol, whereas other services take effect over an insecure channel. An attacker is aware of the protocol design, however, it cannot reveal the user secret key from the user's private space. Also, the attacker can download cloud data bypassing the edge layer. Security analysis. Assume TQ epsilon decision Diffie-Hellman inversion assumption holds in G1, then the proposed KAC-EC is T prime epsilon prime CCA secure in polynomial time T prime with advantage epsilon prime, where QK, QE, QD are the keygen extract decrypt queries and TE, TP are the time for exponentiation and pairing cost respectively. Due to time restriction, the explanation of these claims is omitted. Performance discussion. Figure 4a shows the simulation setup for the proposed protocol, while Figure 4b discusses the typical cloud computing settings. To estimate the performance, we set cloud provider as Google Drive, controller and KGC as two Asus desktop, edge device as one Sony laptop, uploader and downloader two Raspberry Pi Model 3B. Finally, we set the communication at the edge side 10 Mbps via LAN, while on the user side as 1 Mbps via Wi-Fi. For this simulation, we set the file size as 700 MB. Table 1 shows various cryptographic operations overhead under different devices configured as mentioned above. Figure 5a shows a performance orchestration both in sequential and parallel modes, where the ratio indicates the average load of a single edge device for a total 100 different users. Under the KSEEC in figure 5b, DC spent nearly 24 minutes in downloading and decrypting 700 MB encrypted file, while nearly 35 minutes in direct communication with cloud. Table 2 displays individual entities' particular cost, where an edge device requires only 2 minutes to download 700 MB file and to incorporate authorization token in the ciphertext. Figure 6a compares various schemes in terms of cost due to security incorporation. Clearly, we can see that the proposed scheme is efficient than other schemes except the work 11. However, if we see the next figure, work 11 has a significant amount of data latency. Besides, from table 3, we can conclude that the proposed scheme achieves more security features than others. In short, the KSD achieves certain security features about 60% more, enables multiple cloud integration, eases computation burden about 30% less during data sharing and uphold. In summary, we introduced the KAC-EC protocol alleviating the security hurdles in the edge cloud data sharing scenario. The KAC-EC allows multiple owners to securely share multiple files based on the distinct file classes for multiple receivers in multiple remote space. It achieves several promising security elements such as confidentiality, unified access control, anonymity, and revocation. It offers benefits in latency, data security, storage, and access control. In the future, we'll extend this work by enforcing secure caching optimization and scalable load balancing at the edge in a fully untrusted edge cloud context. Here are the references for this work. Thank you very much for your attention. If you have any queries, you may contact me.